Picture this. It is the autumn of 1914. You are standing in the freezing, completely waterlogged mud of a shattered trench on the western front of World War I. The air is so thick with the smell of cordite, blood, and sheer despair that you can actually taste it. Artillery shells are streaming continuously overhead, shaking the earth so violently your teeth rattle amidst absolute, unrelenting chaos. Suddenly, through that chaos, defying the explicit, screaming orders of rigid French military generals, a repurposed civilian delivery truck rumbles straight into the active war zone. The driver stepping out of the mud-spattered cab isn't a seasoned soldier, nor is she a general. She is a 47-year-old woman wearing a simple dark dress. What she carries in the back of that truck changes everything. She has hauled in a heavy dynamo that she personally figured out how to hook up to the car's engine. That dynamo generates the electricity needed for a bulky, fragile machine that produces an invisible, skin-burning ray. She is using that ray to look straight through the mangled flesh of shattered soldiers, pinpointing jagged pieces of shrapnel so the field surgeons do not have to operate blind. She is actively saving thousands of lives. Yet, there is a chilling, deeply tragic flip side to this heroics. As the machine hums and the invisible rays pass through the soldiers, her own bone marrow is quietly, irrevocably being destroyed by the very glowing dust she had discovered in a leaky shed years earlier. Welcome to Legendary Lives Unveiled. If you are captivated by the profound, untold triumphs and tragedies of history's greatest minds, please take a moment to like this video, share it with a fellow history lover, and subscribe to our channel. Your support allows us to keep bringing these epic journeys to life. We are opening up a massive stack of historical archives, deeply personal biographical excerpts, and original, densely written scientific papers to examine the epic, tragic, and monumental life of Marie Curie. Our mission is to uncover exactly how a financially destitute girl, born into an occupied nation that was actively and violently trying to erase her culture, somehow managed to completely shatter the immutable boundaries of classical physics. We must understand how she became the foundational mother of modern oncology, and why she willingly paid the ultimate physical price for the advancement of humanity. To truly grasp the magnitude of the woman who eventually brought the deeply entrenched, highly patriarchal academic establishment of Paris to its knees, we cannot start her story in France. We must start in the crucible that forged her. We must look at the oppressed, suffocating world of her youth, which instilled in her a level of stoic resilience that most people today cannot even begin to fathom. Rewind the clock to the year 1867. She is born Maria Skłodowska in Warsaw. But this is not the independent sovereign Poland we know today. This is Warsaw, firmly trapped within the grip of the Russian Empire. The geopolitical erasure was systematic and utterly brutal. Russian authorities were enforcing Russification policies, actively suppressing the Polish language and outlawing Polish culture. Crucially, for the trajectory of our story, they were absolutely terrified of intellectualism. They understood perfectly well that an educated populace is a rebellious populace. These deliberate, oppressive Russian pedagogical dictates hit her family directly. Maria's father, Władysław, was a highly educated secondary school teacher of mathematics and physics. Because of his pro-Polish sentiments and his quiet but firm refusal to completely bow to the Russian inspectors, he was repeatedly targeted. He was repeatedly demoted and stripped of his high-ranking posts. As a direct result, the family lost their financial security and their comfortable housing. But the detail that truly stands out is that Władysław did not just quietly submit. when the Russian authorities literally banned laboratory equipment in Polish schools because they did not want Polish children learning the scientific method or critical thinking. He did not throw the gear away. He essentially became a smuggler. He packed up the glass tubes, the sensitive scales, barometers, and electrometers, and sneaked them into their crowded apartment. He set them up and literally instructed his children on how to use them. The psychological impact of that on a young child transforms education from a mundane chore into an act of profound intellectual rebellion. In the Skłodowski household, learning wasn't just a pathway to a middle-class career, it was a moral duty. It was a form of nonviolent resistance against an empire that wanted to pretend you didn't even exist. Maria herself later wrote about this suffocating period, noting that the children were constantly held in suspicion and spied upon. She understood from a very young age that a single careless conversation in Polish, or just an imprudent word spoken in front of the wrong neighbor, could result in her father's arrest or her family's total ruin. Beneath this constant low-level terror of the secret police, tragedy struck the family in the most brutal, physical way imaginable. The financial strain meant they had to take in student boarders just to make ends meet, essentially turning their small home into a crowded dormitory. In the 19th century, crowded living spaces inevitably meant disease. When Maria is just 7 years old, her eldest sister Zofia catches typhus from one of these boarders. Typhus is an agonizing, terrifying way to die, bringing high fevers, delirium, and terrible pain. Losing her eldest sister was a devastating blow, but the trauma was compounded almost immediately. Less than 3 years later, when Maria is barely 10 years old, her mother succumbs to a grueling 5-year battle with tuberculosis. It is a disease that literally wastes you away, right in front of your family's eyes. The psychological toll of those sequential, devastating losses on a young, brilliant girl was immense, particularly regarding her faith. Her mother had been a deeply devout Catholic. Watching her mother pray for 5 years, only to die in agony, along with the sheer random cruelty of her sister's death, completely shattered Maria's faith. She abandoned Catholicism right then and there. She became an agnostic, and later essentially an atheist. She learned very early, and very painfully, that the universe is fundamentally indifferent to human suffering. If there was any order, any truth, or any salvation to be found in this world, it wouldn't come from divine intervention. It had to be rigorously proven, measured, and understood through science. This realization made her throw herself entirely into her studies, which became her coping mechanism. She is brilliant. At age 15, she graduates from a girls' gymnasium, the equivalent of a secondary school, with a gold medal for her sheer academic excellence. But here is where she hits a massive, seemingly insurmountable brick wall. Despite her undeniable brilliance and top honors, the University of Warsaw absolutely refuses to admit her, simply because she is a woman. The institutionalized gender discrimination of the Russian Empire in that era was absolute and uncompromising. Higher education for women was considered absurd, even dangerous. Finding themselves locked out of the formal system, Maria and her older sister Bronya turned to an incredible underground network known as the Flying University, or the Floating University. It was a clandestine, illegal network of Polish scholars and scientists who were teaching out of private homes. They were constantly changing locations in the middle of the night, hence the flying or floating name, just to avoid detection by the Tsar's secret police. Imagine being a teenager, sneaking through the freezing alleys of Warsaw at 2 a.m, clutching a chemistry textbook to your chest, knowing that if the police catch you, you could literally be sent to Siberia. This clandestine environment created a scientist who viewed knowledge as something genuinely sacred. It stripped away any sense of academic entitlement. For Maria, studying the natural world wasn't a luxury. It was a hard-fought privilege worth risking her freedom for. The Flying University wasn't just teaching suppressed Polish history or literature. They were teaching modern, cutting-edge science. But as much as Maria loved this underground network, both she and Bronia were pragmatists. They knew that while this secret education was noble, it couldn't provide the formal, internationally recognized laboratory training and degrees they needed to truly make an impact on the world. They needed to get to a place where women were legally allowed to look through a microscope. They needed to get to Western Europe, specifically Paris, which was the epicenter of scientific thought. But they were entirely broke, possessing zero capital. So they sat down and came up with a plan that is remembered as the Sisters' Pact, a beautiful, deeply touching demonstration of their familial solidarity. The agreement was this: Maria will stay behind in Poland and work as a governess. She will take all her earnings and send them to Paris to fund Bronia's medical studies. Then, once Bronia graduates, becomes a practicing doctor, and starts making money, she will reverse the flow and pay for Maria to come to Paris and study at the Sorbonne. For years, Maria puts her own dreams completely on hold. She goes out into the rural provinces to work as a governess. One of her longest and most significant stints is working for the Żurawski family. These were actually distant, much wealthier relatives of her father, living in a rural agricultural area called Szczuki, where they ran a massive sugar beet factory. Hired to educate their children, out in the middle of nowhere, her subversive, rebellious streak continues to flare up. She simply couldn't turn off her deeply ingrained sense of duty to her people. During what was supposed to be her free time, she secretly began gathering the local peasant children, the impoverished children of the factory workers who had absolutely no access to schooling. She brings them into her room and teaches them how to read and write in Polish. This was a strict violation of Russian law. She is risking arrest by the authorities and risking her job with the Żurawski family just to make sure these kids aren't illiterate. Simultaneously, late at night, she is still relentlessly educating herself, reading advanced physics and sociology texts. She even manages to talk a chemist who works at the sugar factory into giving her secret chemistry lessons. Her time in Szczuki ends in profound, lingering heartbreak. She falls deeply, passionately in love with the eldest son of the family, Kazimierz Żurawski. He was home from university and would later become an eminent mathematician in his own right. They were intellectually matched, and they desperately wanted to marry. But when Kazimierz went to his parents to ask for their blessing, they absolutely forbade it. To the wealthy Żurawskis, Maria wasn't a brilliant scientist in waiting. She was just the penniless, inferior, socially insignificant relative who worked for them. Kazimierz, despite his own brilliance, couldn't stand up to the overwhelming pressure of his parents. The engagement was broken, and the relationship was painfully severed. There is an incredibly melancholic footnote to that romance. Decades later, when Maria was globally famous and Kazimierz was an old man, he would reportedly go and sit contemplatively before a large bronze statue of her that was erected in Warsaw. As brutal as that rejection was for her at the time, it hardens her resolve. She realizes she has nothing holding her back anymore. She returns to Warsaw, manages to get some actual hands-on time in a secret chemistry lab run by her cousin, and finally, in 1891, the Sisters' Pact is fulfilled. Bronia is married and established in Paris as a physician, and she sends for her sister. Maria boards a train, crosses the border into France, and as she steps off onto the platform, Maria Skłodowska transforms into Marie, That physical journey marks the beginning of her Parisian metamorphosis. In late 1891, at the age of 24, she formally enrolls in the Faculty of Sciences at the University of Paris, known famously as the Sorbonne. We need to dispel any romantic notions here. Fulfilling the pact and arriving in Paris did not mean she was suddenly living comfortably or enjoying the bohemian café culture. She starts out living with Bronya, but it's an hour's commute by horse-drawn omnibus to the university, and she feels it's wasting precious study time. She moves out on her own, living in extreme grinding poverty. She rents a tiny, freezing little garret, an attic room, in the Latin Quarter so she can be within walking distance of the laboratories. She survives on a daily diet of buttered bread and tea. Sometimes she treats herself to a single egg or a piece of fruit, but that's rare. In the winter, Paris can be bitterly cold, and she cannot afford coal for her small stove. When the temperature drops, she literally opens her trunk and puts on every single piece of clothing she owns at the exact same time, piling coats on top of her blankets just to keep her core body temperature high enough to sleep. The physical deprivation was severe. She was so laser-focused on her mathematical equations and physics textbooks that she would frequently forget to eat entirely, leading to moments where she actually fainted from sheer hunger and exhaustion in the middle of the library. Her brother-in-law had to come check on her, force-feed her a steak, and scold her into taking care of herself. Imagine the sheer force of will. Despite the starvation, despite shivering through the night, and despite studying highly complex mathematics and physics in French, her second language, she absolutely dominates her classes. In 1893, she is awarded her degree in physics, ranking absolutely first in her class. The very next year, with the help of a small Polish fellowship, she completes a second degree in mathematics, ranking second in that class. It is a staggering display of intellectual dominance, and it is. In that year, 1894, while she is desperately looking for a larger laboratory space to conduct a commissioned study on the magnetic properties of various steels, that she is introduced to a man who will change her trajectory forever. We must pause and establish who Marie Curie was, because he was not just some random academic lab manager. He was already a highly established famous physicist in his own right, almost a decade older than Marie. He and his brother Jacques had already made massive contributions to science. They discovered the piezoelectric effect. Piezo comes from the Greek word to squeeze or press, and this discovery remains foundational for modern technology. Pierre and his brother found that when you apply mechanical pressure to certain crystals, like quartz, they generate an electrical charge. Conversely, if you apply an electrical charge to them, they subtly change shape or vibrate. If you are wearing a quartz watch right now, or if you use a microphone, or even an ultrasound machine, you are relying directly on Marie Curie's discovery of the piezoelectric effect. He was a giant of physics in his own lane. This makes their meeting one of the greatest serendipitous collisions in the history of human knowledge. They bond almost immediately over their shared, almost monastic devotion to scientific inquiry. Marie was actually planning to return to Poland permanently, to care for her aging father and contribute to her homeland. And she actually went back to Warsaw briefly. But Pierre wrote her incredibly passionate letters, pleading with her to return to Paris so they could pursue their scientific dreams together. Tragically, academic ironies forced her hand. She applied for a university position at the Jagiellonian University in Krakow. Despite being highly qualified, with 2 degrees from the Sorbonne, she was flatly rejected. The academic gatekeeping was universal. They simply would not hire a woman. Realizing that Poland would not allow her to reach her potential, she accepted Pierre's proposal and returned to Paris. They were married in a very simple civil ceremony in 1895. She did not even buy a wedding dress, wearing only a dark blue outfit that she could reuse as a laboratory smock. Marie and Pierre did not just feel like a married couple. They felt like the perfect chemical reaction. They were two highly reactive elements. Pierre brilliant, intuitive, and inventive, and Marie relentless, mathematically rigorous, and intensely driven. Stable on their own, combined in the laboratory, they created an unstoppable, world-changing release of energy. What is so deeply fascinating, especially when analyzing late 19th century gender dynamics, is the absolute egalitarian nature of their partnership. Pierre recognized Marie's genius so implicitly, and with such a lack of ego, that a few years into their marriage, he completely abandoned his own highly successful, career-defining research on crystals. Seeing what she was onto, he stepped aside to become her assistant, her collaborator, and her sounding board. He did not try to eclipse her or steal her credit. He elevated her. This set the perfect foundation for what happens next. It is 1897. Marie has her degrees, she has a supportive genius partner, and they have just had their first daughter, Irene. She needs a topic for her doctoral thesis. The timeline here is crucial. In 1895, Wilhelm Röntgen discovered X-rays, which captured the entire world's imagination because you could suddenly see the bones inside a living hand. The following year, 1896, Henri Becquerel was experimenting with uranium salts, trying to see if they emitted X-rays after being exposed to sunlight. In a famous accident, he left the uranium salts in a dark drawer, wrapped up with some unexposed photographic plates. When he developed the plates, he found they were fogged. The uranium was emitting some kind of mysterious, invisible ray entirely on its own, without needing sunlight. He called it spontaneous radiation. But the wild part is that the scientific community looked at Becquerel's rays and said that, while mildly interesting, it was not as cool as X-rays, and they largely moved on. Marie looks at this overlooked phenomenon and is profoundly intrigued. She decides her thesis will investigate whether this strange energy is exclusive to uranium, or if other substances in the natural world do the exact same thing. To do this, she could not rely on photographic plates that were too subjective. She needed highly precise, quantifiable measurements of the electrical charge in the air caused by these rays. So, she turns to an instrument invented 15 years earlier by Pierre and his brother, an incredibly sensitive electrometer, which utilized the very piezoelectric quartz crystals they had studied. She is basically using a machine that measures tiny electrical currents in the air. If a rock is shooting out invisible energy, it electrically charges the air around it, and this machine detects that charge. She starts feeding every mineral she can get her hands on into this machine. Here is where the earth-shattering moment happens. She tests hundreds of various minerals, compounds, and salts, discovering that two specific uranium ores, pitchblende and chalcolite, also known as torbernite, were behaving very strangely. The electrometer showed they were far more active, far more energetic than pure uranium itself. The logic here is the leap of genius. If the raw, dirty ore is shooting out more energy than the pure uranium you extract from it, there is only one logical conclusion. There must be something else hiding inside that rock, something undiscovered and exponentially more active than uranium. Her genius was not just in realizing there was a new element, it was in defining what this energy actually was. This is the paradigm shift that completely broke classical physics. Before Marie Curie, the established scientific consensus was that the atom was like a microscopic, solid, indivisible billiard ball. It was the fundamental, unchangeable building block of the universe. You could combine them to make molecules, but the atom itself was solid and eternal. Marie completely obliterates that model. After exhaustive testing, she hypothesizes that this mysterious radiation was not the result of some chemical interaction between molecules reacting to each other. She boldly states that the radiation must be coming from the atom itself. It is an intrinsic atomic property. The atom was essentially breaking down, shooting pieces of itself out as energy. She even coins the term for this atomic decay, radioactivity. By proving that atoms could emit energy and decay, she proved the atom was not indivisible. She essentially ripped open the billiard ball and showed the world that there was a universe of chaotic energy inside. She opened the door to modern nuclear physics, nuclear power, and atomic medicine. But a theoretical hypothesis in physics is not enough. The chemists of the world demanded physical proof. If there were undiscovered radioactive elements in that pitch blend, she had to isolate them, hold them in her hand, and weigh them. The actual grueling physical logistics of what she had to do next turns the story into a brutal test of endurance. To prove this invisible theoretical property of the atom, she and Pierre essentially spent years boiling toxic dirt in a freezing shed just to get a microscopic glowing speck of powder. The university refused to give them a proper laboratory. Instead, they were offered a disused, leaky, unventilated shed that had previously been used by the medical school as a dissecting room for cadavers. It had a glass roof that turned it into a suffocating greenhouse in the summer, and in the winter, it was so freezing that the water in their equipment would turn to solid ice. Their raw material is pitchblendy, which was heavily mined in places like Bohemia, primarily to extract uranium for coloring glass. It was expensive, and they could not afford pure ore. Marie, being incredibly resourceful, realizes that if the uranium has already been extracted from the rock, the mysterious new elements must still be trapped in the discarded waste dirt, the slag. She negotiates with the Austrian government to buy tons of this worthless, muddy waste product for essentially the cost of shipping. When it arrives at their shed, the electrometer confirms her theory. The waste dirt is incredibly radioactive. Then begins a period of physical labor that borders on madness. She is not just a scientist anymore. She is acting like a heavy industrial factory worker. She is using a chemical process called fractional crystallization, processing this toxic waste in massive 20-kilogram batches at a time. Pitchblende is an incredibly complex, messy mineral containing up to 30 different known elements mixed together. Imagine a massive bucket filled with a mixture of fine sand and sugar. If you pour water into that bucket, the sugar will dissolve into the water, but the sand will remain solid. You can then pour off the sugar water, effectively separating the two materials. She was doing a highly advanced chemical version of that, but instead of sand and sugar, she is dealing with heavy metals, strong acids, and invisible radiation. To isolate the unknown substances, they would haul these 20-kilogram sacks of dirt into the shed. They dissolved the sludge in harsh acids, boiled it, filtered it, and precipitated it with various chemicals. For example, she might add a chemical that causes a specific known element to turn into a solid powder at the bottom of the vat, which she could then filter out. As this fractionation process progresses, she would boil the remaining toxic liquids down to form tiny needle-like crystals. She is doing this while standing over massive boiling cast iron vats, physically stirring the heavy, sludgy liquid for hours on end with a heavy iron rod that was almost as tall as she was. The fumes of hydrogen sulfide and acid fill this unventilated shed. Her hands are blistered, and her eyes are stinging. At every single step, after every boiling and filtering, she would run back to the electrometer to measure the radioactivity of the resulting crystals and the remaining liquid. She was relentlessly tracking the invisible energy, discarding the inactive portions and keeping the highly active ones, narrowing the chemical haystack down to find the radioactive needle. She isolates these fractions down and down for months on end, until finally, the breakthrough arrives. In July 1898, they publish a joint paper announcing the discovery of a brand new, highly radioactive element found hidden in the bismuth fraction of the pitchblende. She names it polonium, which we must recognize was a deeply aggressive political statement wrapped in the scientific discovery. Poland did not exist on the official map of Europe. It had been partitioned and erased by Russia, Prussia, and Austria. By naming the very first element she discovered polonium, she literally forced the entire international scientific community, including the Russian scientists who read the journals, to speak the name of her occupied, erased homeland. It was an act of profound scientific diplomacy and patriotic defiance. Just months later, in December 1898, they announced the discovery of a second, even more powerful element found in the barium fraction. They name it radium, from the Latin word for ray, because this substance was millions of times more radioactive than uranium. It was so energetic that the concentrated salts actually glowed in the dark with this eerie pale blue light. The scientific implications of these two papers were monumental. They had proven the existence of entirely new elements, based solely on their radioactive signatures. But the scientific establishment moved slowly, taking years for the work to be fully processed and recognized by the global community. Finally, in June 1903, she presents her doctoral thesis at the Sorbonne, becoming the first woman to receive a PhD in the physical sciences in France. That same year, the pinnacle of scientific achievement comes knocking. The Nobel Prize in Physics is awarded in recognition of the extraordinary services rendered by the discovery of radioactivity. Here is where the deeply entrenched systemic sexism of the era rears its ugly head again. The French Academy of Sciences submitted the official nominations to the Nobel Committee, and they intentionally, deliberately, left Marie Curie's name off the document, nominating only Henri Becquerel and Pierre Curie. They literally tried to write her out of her own paradigm-shifting discovery. Fortunately, a sympathetic member of the Nobel Committee, an advocate for women in science named Gustave Mittag-Leffler, secretly wrote a letter to Pierre alerting him to this deliberate exclusion. Pierre's furious reaction tells you everything you need to know about his character. He immediately wrote back to Stockholm, stating unequivocally that a Nobel Prize that did not include Marie was a farce. He insisted that he would publicly refuse the prize unless she was equally and officially recognized for her fundamental, foundational role in the discovery. Faced with the embarrassment of the winner rejecting the award, the committee finally relented and added her name. Thus, Marie Curie became the first woman in history to win a Nobel Prize. They win the prize, get global fame, and receive a substantial amount of prize money, which they immediately use to pay back massive laboratory debts, financially assist her family back in Poland, and hire a lab assistant. You would think, after the starvation, the shed, and the sexist gatekeeping, they have finally made it to the mountaintop. But the triumph of the 1903 Nobel is almost immediately followed by a shattering, incomprehensible personal tragedy that will thrust her into darkness and demand an entirely new level of unyielding resilience. In April 1906, Pierre is walking across the Rue Dauphine in Paris during a heavy rainstorm. Holding an umbrella, his mind is likely lost in scientific thought. He steps out from behind a cab, slips on the wet cobblestones, and falls directly into the path of a heavy horse-drawn military wagon carrying 6 tons of uniforms. The rear wheel crushes his skull, and he is killed instantly in a sudden, violent, and utterly senseless accident. Marie is utterly devastated, losing her husband, her deeply devoted partner, the co-parent to their two young daughters, Irene and Eve, and her closest, most trusted scientific collaborator. In the span of a heartbeat, she is entirely alone in the world. The grief she documented in her private journals is harrowing to read. She addressed letters to him as if he were still alive, detailing her absolute despair. However, the university, realizing they had lost a titan, made an unprecedented move by offering Marie the chair of physics that had been created for Pierre. She accepted it, believing she had a duty to continue their work. In doing so, she became the first female professor in the 600-year history of the Sorbonne. But the scientific establishment is not done testing her. Not all chemists believe that radium is actually a genuine, standalone element. People like Lord Kelvin, an absolute titan of classical physics, and the man who the Kelvin temperature scale is named after, publicly expressed skepticism. He argued in the press that radium might just be a chemical compound composed of lead and helium. This public skepticism from such a prominent figure forced Marie into a highly defensive corner. In the rigid world of 19th and early 20th century chemistry, there was an ultimate trump card. The indisputable proof of a new element's existence was to isolate it as a pure, unalloyed metal and determine its exact relative atomic mass. As long as she only had radium salts, like the radium chloride she had extracted in the shed, the doubters could always point to it and claim it was just a molecular compound of existing elements. She had to strip everything else away to prove them wrong. Imagine the immense crushing pressure she is under right now. She is actively, deeply grieving the sudden violent death of the love of her life. She is raising two young daughters as a single mother. She is facing a hostile, chauvinistic academic press that wants to see her fail. Simultaneously, she is stepping into the laboratory entirely alone to perform what is arguably the most precise, unforgiving chemistry in human history, just to silence her doubters. To understand the magnitude of what she accomplished in 1907, we have to look at the staggering precision required for the highest standard of empirical proof. She starts the experiment with 0.4 grams of what she believed was perfectly pure radium chloride. Considering she had to process tons of pitchblende just to get a fraction of a gram, that 0.4 grams was essentially the most precious substance on Earth. She dissolves this tiny amount of salt in pure water mixed with hydrochloric acid. Then she uses an instrument called de Marcy's spectrograph to test it. Think of a spectrograph as a machine that reads the chemical barcode of the universe. When you take an element, heat it up until it sparks, and pass that light through a prism, the light splits, creating very specific, sharp lines of color at exact wavelengths. Every single element on the periodic table has a unique set of lines, its own unique barcode. If you burn neon, you get specific lines. If you burn oxygen, you get different lines. The wavelengths are measured in a unit called angstroms. Barium, an element chemically very similar to radium, has a very bright, distinct line at 405 to 4.2 angstroms. Radium has its own distinct line right next door at 400 to 533.3 angstroms. Marie needed her radium to be absolutely 100% pure, so she uses the spectrograph to look at the spark of her sample. If she sees the barium line shining brightly alongside the radium line, she knows her sample is contaminated, because barium and radium are so chemically similar. Separating them is a nightmare. Like trying to separate a cup of salt from a cup of slightly different salt. When she sees the barium line in the spectrograph, she has to undergo fractional precipitation again, using alcohol over and over until the barium line completely vanishes from the spectrograph. When she is finally satisfied that there is zero barium contamination, she has to weigh the pure radium chloride. But there is a massive problem. Radium chloride is hygroscopic, meaning it aggressively absorbs water vapor straight out of the ambient air. If it absorbs water, it gets heavier, which ruins the atomic mass calculation. She has to dry it out and weigh it instantly. She heats the sample above 100 degrees Celsius to evaporate all the water. Then she transfers it to a highly specialized, incredibly fast-settling scale called an aperiodic balance. The deeply poignant part of this is that the specific aperiodic balance she was using was an instrument that Pierre had custom designed and built for her before his death. Even in this incredibly stressful solo experiment, Pierre's genius and his support are still right there on the workbench with her, helping her find the answer. Using Pierre's scale, she weighs the pure radium chloride. Then she dissolves the salt again, adds a warm solution of silver nitrate to cause the chlorine to bond with the silver and precipitate out as silver chloride. She carefully filters this out, dries it, literally burns the filter paper to ash, heats the silver chloride to its melting point, and weighs it. By knowing the weight of the original radium chloride and the weight of the silver chloride she extracted, she can use the known atomic weights of chlorine and silver to algebraically deduce the exact atomic weight of the radium. She does not just do this once. She runs this incredibly delicate, terrifyingly precise multi-step process 3 consecutive times, risking her precious 0.4 grams of radium every single time. The mathematical values she calculates for the relative atomic mass of radium are 226.35, 226.04, and 226.15. This averages out to 226.19, leading her to conclusively state to the scientific world that the atomic mass of radium is 226.2. This is astonishingly accurate even by today's computerized standards. Because she was so obsessively meticulous, she was literally distilling her own pure water to make her own hydrochloric acid and redistilling the alcohol to prevent any spurious sulfate residues. She even had to switch from using glass containers to pure platinum containers because the radiation from the radium was literally eating the glass. Because of all this, the scientific community had no choice but to bow to her data. She definitively proved radium was a unique element, silencing Lord Kelvin. Radium secured its permanent place on the periodic table, and for this monumental act of solo chemistry, in 1911, she is awarded the Nobel Prize in Chemistry. This makes her the first person, and to this very day, the only person in history to win Nobels in 2 different scientific fields. But because the world is deeply unfair, even this monumental triumph is dragged through the mud by an ugly, vicious public scandal known as the Langevin scandal. Just days before the 1911 Nobel was officially announced, the deeply conservative, sensationalist French press got hold of stolen love letters, revealing that Marie, a widow for 5 years, was having a brief romantic affair with Paul Langevin. Langevin was a brilliant physicist and a former student of Pierre's. He was married, though estranged, and living apart from his wife at the time. The press reaction wasn't just gossip. It was a targeted, xenophobic witch hunt. They painted her as a foreign Jewish homewrecker. Even though she was raised Catholic and was agnostic, they used Jewish as a slur in the deeply anti-Semitic climate of France following the Dreyfus affair. Mobs actually gathered outside her house, terrifying her daughters. The scandal was so severe that a member of the Swedish Academy formally suggested she should not come to Stockholm to accept the prize, to spare them the embarrassment. Her response to that letter is one of the most defining moments of her character. She wrote back, stating essentially that the prize had been awarded for the discovery of radium and polonium, and she believed there was no connection between her scientific work and the facts of her private life. She refused to let them dictate her worth based on tabloid gossip. She packed her bags, traveled to Stockholm, stood in front of the King of Sweden, and claimed the prize she had bled for. But her victory lap is cut short. Having conquered the mysteries of the periodic table, the world suddenly fractures in 1914, and Europe plunges headfirst into the meat grinder of World War I. Marie, watching the devastation, pivots entirely. She redirects her fierce exactitude and scientific authority away from theoretical physics and points it directly at the bloody battlefields. When the war broke out, the French military health service was catastrophically unprepared for the realities of modern artillery warfare. By late 1914, Marie realized a massive fatal failure in the medical logistics. The new field hospitals and casualty clearing stations near the front lines had almost zero radiological installations. In 1914, X-ray machines were massive, heavy, highly fragile pieces of equipment confined to the basements of major city hospitals. This meant that when a soldier was brought in with his leg shredded by a German artillery shell, the surgeons had no way to see where the jagged pieces of metal were lodged in his flesh. Facing this horrific systemic failure, Marie Curie is about to execute an emergency operation that will drag her into the bloodiest mud of human history. Because they could not locate the shrapnel, surgeons were forced to perform blind surgeries. They were probing open wounds with unsterilized fingers, which caused massive infections, or they were simply amputating limbs entirely, just to save the soldier's life. The mortality rate was horrific. Marie looks at this systemic failure, and she acts like a modern ruthless tech founder, executing an emergency pivot. She doesn't just sit in a lab and try to invent a smaller X-ray tube. She realizes the problem is logistics, and she builds an entire medical supply chain from scratch. She conceives of, designs, and deploys the world's first mobile radiological cars, which the wounded soldiers would eventually, affectionately, nickname the Petites Curies, or Little Curies. Her mechanical and technical ingenuity here cannot be overstated. The primary obstacle for creating a portable X-ray machine isn't the tube itself, it's the power source. You need a massive, consistent amount of electricity to run a Crookes tube to generate the X-rays, and you cannot just plug it into a tree at the front lines. Marie figures out how to adapt a heavy electrical dynamo, a generator, and mechanically connect it directly to the petroleum-powered engine of the Renault delivery truck itself. The car drives to the front lines, parks outside the medical tent. They leave the engine running to turn the dynamo, and the dynamo generates the voltage needed to power the X-ray machine inside the hospital tent. It was a perfect, self-contained mobile hospital unit. But conceptualizing it was only the first step. The French government bureaucracy, entrenched in military tradition, was agonizingly slow and dismissive of this civilian woman's ideas. She bypassed them entirely. She secured private funding from the Union of Women of France, went to her wealthy Parisian acquaintances, the very aristocracy that had shunned her during the Langevin scandal, and convinced them to donate their luxury civilian vehicles. She then wheedled and bullied car body shops into converting these luxury cars into utilitarian radiological vans. We must dwell on the profound personal transformation she undergoes here. She is a Nobel-winning theoretical physicist, not a medical doctor, and certainly not a mechanic. But she realizes that if she builds these trucks, she needs people to run them. Because all the men are fighting, she gives herself a brutal crash course. She teaches herself human anatomy so she can actually read the X-rays and point the surgeons to the bullets. She teaches herself auto mechanics so she can clean a flooded carburetor or change a heavy tire in the freezing mud. She actually has to learn how to drive a car, and then accompanied by her 17-year-old daughter, Irene, who refused to be left behind. She drives these homemade trucks straight into the artillery zones. Contextualizing this within the history of early 20th century medicine is vital. This wasn't just a temporary wartime patch. This effort fundamentally established radiology as an indispensable frontline medical discipline. And we have to consider the severe emotional and psychological toll this took on her. Marie and young Irene were witnessing the absolute worst horrors of industrial warfare, with physically staggering wounds caused by shrapnel and machine gun fire. But she doesn't break down. She deliberately locked her emotions away, maintaining a stoic, almost icy clinical detachment. She meticulously recorded patient data, calculated exposure times, and processed the photographic plates specifically so she wouldn't traumatize Irene or cause panic among the wounded, terrified soldiers. She was the calm center of the bloody storm. Eventually, she outfitted 20 of these mobile vans and personally oversaw the construction of 200 permanent radiological rooms at fixed field hospitals behind the lines. Historical records estimate that over 1 million wounded soldiers were treated using the mobile units and field stations she established. She even went a step further, taking her own personal, incredibly valuable supply of pure radium, the radium she had isolated by hand, and using it to produce radon gas. She captured this gas in tiny, hollow glass needles and distributed them to hospitals to be inserted directly into infected tissues to sterilize them and destroy early tumors. And yet, despite saving 1 million men, despite giving up her time, her research, and her health, she never received a single formal commendation, medal, or recognition from the French government for her war efforts during her lifetime. This serves as a stark, infuriating reminder of the persistent marginalization she faced. She was a hero, but she was still a foreign-born woman in a male-dominated empire. However, the war did accomplish one profound thing for her science. It proved, beyond any shadow of a doubt, the immense practical medical value of radiation. It shifted her internal focus from pure theoretical physics to the institutionalization of this science for public health, which becomes the final enduring mission of her life. She had actually founded the Radium Institute in Paris in 1914, right before the guns fired, and later, deeply honoring her roots, she helps establish a sister institute in her native Warsaw in 1932. But to run these institutes and research cancer treatments, she needs more radium. Radium is now the most expensive substance on planet Earth because it is being manufactured by massive corporations for profit. This economic reality highlights a crucial, defining historical choice she and Pierre made decades earlier. Back in 1898, when they first isolated radium and figured out the complex fractional crystallization process, they were advised by friends to patent the method. If they had patented it, they would have held a monopoly on the production of a substance that the whole world suddenly wanted. But they explicitly, vehemently refused and published all their methods freely. Marie stated, "Radium is a chemical element, a property of all humans." She firmly believed that foundational scientific discoveries belong to humanity, not to corporate monopolies. And they walked away from unimaginable wealth. The bitter, tragic irony of her life is that by giving the process away to the world, the corporations took it, monetized it, and drove the price up so high that Marie Curie herself couldn't afford to buy it for her own cancer research lab. By the 1920s, a single gram of pure radium cost around $100,000, which is roughly equivalent to $1.5 million today. So, in 1921, this deeply introverted, tired, aging scientist is forced to undertake a massive, exhausting PR tour of the United States. An American journalist named Marie Maloney realized Curie's plight and organized a massive crowdfunding campaign among American women. The tour was a spectacle, where Curie was mobbed by reporters at the docks, forced to attend endless high society galas, and given honorary degrees. The sheer pageantry of it exhausted her, but she endured it all because at the end of the tour, President Warren G. Harding presented her with a lead-lined mahogany box containing exactly 1 gram of radium. She endures the flashbulbs and the endless handshakes just to get her hands on more of the very substance that is silently, slowly killing her. By this time, the physical toll is undeniable and highly visible. By the late 1920s and into the 30s, the decades of unprotected radiation exposure finally catch up with her. She suffers from severe blinding cataracts, experiences chronic debilitating fatigue, and her fingertips are hardened and covered in painful, unhealing burn lesions from handling the radioactive materials with her bare hands. The insidious danger of ionizing radiation simply wasn't fully understood in the early days. They knew X-rays could burn the skin, but they didn't realize that gamma rays were penetrating deep into the bone, shattering the DNA in the marrow. On July 4th, 1934, at the age of 66, Marie Curie dies at a sanatorium in Passy, France. The official cause of death is aplastic pernicious anemia, because her bone marrow had been so thoroughly destroyed by the radiation that her body could simply no longer produce new red or white blood cells. When we examine her death historically, we can view it through the lens of scientific martyrdom. Her selfless choice to prioritize open science and frontline medical care over extreme personal wealth or safety lay the direct, unshakable foundation for modern radiation therapy and oncology. By making the processes public, she accelerated global research into using radiation to shrink tumors. She literally died so that a technology could be born that saves millions of lives today. And what's truly beautiful is that her legacy isn't just in the abstract science. It's tangible, living on in her family in a way that is almost genetically astonishing. Her eldest daughter, Irene, the teenager who was there in the mud of the trenches operating the X-ray machines with her, becomes a brilliant physicist in her own right. In 1935, just 1 year after Marie's death, Irene wins the Nobel Prize in Chemistry for discovering artificial radioactivity alongside her husband, Frédéric Joliot. We cannot overlook her younger daughter, Eve, who carved her own fiercely independent and remarkable path. While Eve did not pursue the sciences, she was a brilliant journalist and an intrepid war correspondent during World War II. In 1937, she wrote the definitive, deeply moving, and globally successful biography of her mother, titled simply Madame Curie, which cemented Marie's legacy in the public consciousness. Eve later married an American diplomat named Henri Labouisse, when Labouisse was the executive director of UNICEF. He accepted the Nobel Peace Prize on the organization's behalf in 1965. Eve herself traveled to over 100 developing nations to champion children's health, living an extraordinary life to the age of 102. If you tally it up between Marie, Pierre, Irene, Frederick, and Henry, the Curie family legacy encompasses an unbelievable 5 Nobel Prizes. Marie herself receives one final, unparalleled honor that transcends science and enters the realm of national mythology. In 1995, her remains, along with Pierre's, are exhumed from their quiet cemetery and moved with full state honors to the Pantheon in Paris. The Pantheon is the grand domed mausoleum reserved strictly for the resting place of France's most revered national heroes, people like Voltaire, Rousseau, and Victor Hugo. Marie Curie becomes the first woman in history to be entombed there, entirely on her own merits. During the exhumation, there was a truly crazy, fascinating detail regarding the radiation testing of her remains. When they opened her coffin, they brought in radiation detectors, expecting her bones to be highly radioactive from all the radium she handled. But they weren't. The radium levels were relatively low, which definitively proved that it wasn't the glowing radium in her lab that ultimately caused the fatal anemia. It was the massive, acute, unshielded X-ray exposure from the thousands of hours she spent operating the Petites Curies in the field hospitals during World War I. She truly died for the soldiers she saved. However, her laboratory notebooks from the 1890s, the ones where she recorded the fractional crystallization, are still dangerously radioactive. The notebooks, her cookbooks, and even the furniture from her house absorbed the radon gas and the radioactive isotopes. Today, her original notebooks are considered national treasures, but they are kept strictly in lead-lined boxes at the National Library in France. If a scholar wants to study them, they have to sign a waiver and wear protective anti-radiation gear. Her words, quite literally, still radiate the raw energy of her discoveries. She dismantled the invisible structure of the universe, and she harnessed that terrible power specifically to alleviate human suffering, which leaves us with a profound, lingering question to mull over as we wrap up our time together. We talked about her refusal to patent radium, but what if Marie Curie had patented it? If she had locked down the intellectual property, she would have instantly become one of the wealthiest women on the planet. Could those billions of dollars have been used to build modern, heavily shielded, state-of-the-art laboratories that might have protected her body and saved her life? Or would the corporate gatekeeping of radioactivity have choked off the research? Would it have delayed the development of life-saving cancer treatments by decades, costing millions of lives? It is a heavy, unanswerable question, but it stands as a profound testament to a woman who valued the alleviation of human suffering far above her own life, her own safety, and her own prosperity. If you were inspired by the relentless dedication of Marie Curie, make sure to like, share, and subscribe to Legendary Lives Unveiled, so we can continue bringing you the untold stories of history's greatest minds. Leave a comment below, sharing your thoughts on her ultimate sacrifice. Keep exploring, keep questioning, and we'll see you next time.